Hello, everybody. My name is Jaana, and today I will be actually talking about failure. I work at Google, and I'm coming from a monitoring background. It's actually a shame that this is first of all, I will have to confess that it's a shame that this is my first time in Marbella, and it's for a conference. So anyways, when I proposed this talk, I actually explicitly wanted to call out that the servers are going to fail. But then I realized that, hey, it doesn't mean that serverless is not going to fail either. So I just want to make a slight, modification. I just want to call this as, and retitle it to, systems are doomed to fail. So how many of you have ever worked in a culture where failure is not accepted? I did. I worked for a company, and I ended up working from 10 a.m. to 10 p.m. every day for weeks when there's an outage, and we were just constantly putting water on fire. And I think once I just kind of start to work for a company where failure is accepted, I realized that it really impacts the engineering culture at a fundamental level. Failure is not just accepted, it's just seen as a norm, even internalized enough to be seen as business as usual. So failure is not an exception. We enhance our systems with new features, new capabilities, and incidents and outages are inevitably going to happen given the scale and the velocity of the change. Unless you have some really formalized process of monitoring, debugging, and learning from failure, this might become an issue because failure is accepted and you're not planned for that. Incidents can easily multiply in complexity, and they may even cascade and overwhelm the entire system, and as well as the people, operators, and software engineers. So regardless of the scale, change is inevitable. I've seen people saying that oh, we haven't touched this code, so it should just work fine. But there's no such thing that I haven't touched this code for a century and it's still going to work. Environment changes, right? Dependencies change. Change is not just about your stack. Change is about everything you depend on. So change is inevitable. And having the wrong, I think, attitude against failure is not a solution. Instead, we want to see failure more as expected. But how? Lots of people are asking me, hey, is it about the tools? Is it about the process? Is it about the way, the technical mindset? Is it about the culture of the company? I think it's all of it. We need to accept first, things are doomed to fail, and we need to plan for failure. So when you don't plan, everything is constantly on fire, right? Your users are not happy, and people working for your company are just here in this point. And there's no time to focus on new valuable projects. You're just constantly trying to spend your time to put water on fire. So certain people end up becoming blockers at this point because they have a lot of knowledge about the stack, or they are really good in debugging. This has been a case for me. We had one person who was really good in debugging, and we would just put all that type of work as soon as there's an outage, and that person got really burned out really quickly. And I think one of the most critical things is as soon as you are on fire all the time, your release velocity decreases. It's quite risky to embrace change, right? You don't want to push more stuff. You just create this culture of putting anything new out there is risky and may end your career. So you don't, people end up leaving the companies really quickly because they got burned out. It's not just a burnout because of the constant pressure. It's also hey, I can't really work on anything impactful because, I kind of feel like I am in a risky position all the time. This is one of the main reasons that we embrace failure rather than assuming that it's an unlikely event. The core of, I think, embracing failure requires these three topics to be covered very, very comprehensively, and I will briefly talk about all of them. So the first one is monitoring. This is a way to say that a system is working as sufficiently as possible. You may actually have more formal definitions about it, and I will come back to that later, but I think in summary, it's just about telling if a system is working as sufficiently and take action when there is failure. Debugging is all these like methods and tools that kind of like help you to figure out what is going on. This is especially critical when there's an outage. You need to plan for debugging as well. It's not just about being able to tell, it's also being able to have insights about what is going on. And the next thing is, I've seen a lot of people not doing this at all, and it's about having postmortems around, the entire postmortem culture. This helps you to iterate and improve, so you can have like actually like more insights about what happens in the past, and you can learn. And we can have better technology and processes to build more reliable and resistant systems. So I said that monitoring is being able to say if something is working or if something is broken. To formalize this, we actually set some objectives for availability. And what availability means is, a user cannot really tell if something is broken. And we want to make sure that, these objectives are good enough to reflect the user expectation. So objectives shouldn't be overdone. I've seen people coming up with ideas like, oh, we should be up, all the time, 100% of the time. That's just not possible. You're actually when you're setting those over high objectives, you're making monitoring more of a toil. So you just get alerts all the time, and your operators learn not to look at it because there's no value, right? Having 100% uptime. So if there's a lot of toil, operators will start not to care. You need to be careful about how you set the objectives. So some of the objectives are I can give you some examples. You can say 99.99 of all the requests will return in 1 millisecond, and then alert if there's something goes wrong. It's above 100 millisecond. Or you can say that 99% of the requests should return with an HTTP 500 response, so the server doesn't crash. So it is kind of you set these objectives and you tweak these numbers to figure out what reflects the user experience and what is good enough. And it's a process of its own. So once we set these objectives, we can set alerts to capture, the outages. Monitoring systems will alert and, page if the objective is not set. Don't be excessive about alerting as well. The more alerts, not the better it is, and it's about, setting the objectives right in the first place. If alerts are not, important or not actionable, operations will start on seeing them. This means, they will generally react less to the actual outages because they are overwhelmed by the noise. And encounter how new releases and canaries and all that stuff is impacting the reliability. Your reliable signals might be slightly off when you're pushing new things because your release velocity is just directly impacting the quality of the reliability signals. So it's always a trade-off between how stable you are and how experimental you want to be. And the goal is to keep the alert quality high without giving sacrifice a lot from the user experience. Now I want to switch a little bit to the debugging, because debugging comes into play mainly for troubleshooting failure. But debugging can be also a learning tool, which is not something I'm going to cover in this talk. Debuggability, because it allows self-descriptive systems. The more debuggable a system is, the less we rely on learning it from documentation or code or configuration. But generally speaking, in this case, debugging is going to enable us to troubleshoot the issues. And debugging is also going to help us to do more data-driven decisions when it comes to outage. Debugging is actually essentially a collaborative process. Nobody really talks about it, but I think this is the most important aspect of debugging. You rely on different escalation paths and people. Operators often seem to just react to a case themselves initially. They go through all, debugging signals. When I say debugging signals, these are typically logs, traces, that type of stuff, and they narrow down the problem. And once the problem is self-contained, it's possible to debug further and escalate it to the respective teams. So when designing debugging aspects of a team, you need to actually think about it as a collaborative process. You need to think about the organization, you need to think about the people involved. And debugging methods and tools come in different flavors, and it's the consistency and the continuity is really important. Jumping from, for example, logs to traces should be, without friction, is really crucial. There's an outage, everything is on fire. You just don't have a lot of time to think about your tooling. You just want to make sure that you have the whole picture as easy as possible. For example, if there's an incident, you want to be able to retrieve some collected data from a time window, and you want to be able to consistently break it down with some labels, for example, all across your different signals. And so you can analyze and understand and go deeper. The last component is the postmortems, and this is not a really common practice yet, but it's a really important aspect, because the goal of a postmortem is making sure that the incident is documented. Postmortems includes a lot of details about what contributed to the problem, what went well, what went wrong, and how to get to the solution. And as well as the details on what type of processes and systematic changes or contributions can be done in order not to repeat this incident again. So this is what a this is a postmortem example from the SRE book, if you have seen it. It explains first the details of the impact, and then it summarizes in the end the root causes. And postmortems usually also include some of the steps in order to avoid similar issues. During an incident, what is usually happening is there's a collaborative doc. It's shared between the people who are involved in the incident, and they're collecting all that knowledge about the troubleshooting process on the same doc. Then you actually come up with you figure out, you summarize the root cause, and you list all the action items and ways to track that work. And you often create a digest list of things that you have learned. This is a really interesting aspect, because the lessons learned in the postmortems are not just about the negative things. It also points out what is positive. So this is a good way over time to learn about the good practices, because you're collecting all these these are the positive things that we learned over time. So the postmortem culture at my company is entirely blameless, and we think that it can be entirely blameless, because the point is not really blaming the people when there's an outage. The point is being able to identify the problems. Blameless culture is originated originally in healthcare and aviation industry, because the failure there means usually fatal incidents. You're killing people, so it's just not really nice to point fingers. And when postmortems are blameless, it really changes the culture. It changes the culture where taking responsibility and collaboration is possible. It is really intimidating to me that I need to put myself in a situation and I take risks in order to contribute to the solution, right? But if nobody is actually blaming me, I can be more relaxed about that. So it creates this culture where there's less tension and people prefer to contribute and bring light to the issues rather than fearing of being ashamed. So regardless of the size of your company or project, debugging often requires multiple people to be involved. It sometimes actually crosses among multiple organizations or companies, because our tech stack is usually very complex and includes a lot of different components. And issues often cross multiple sub-projects and teams, even if you're in a small self-contained situation. Failure planning, that's why, needs to be designed for collaboration. So here are some of the few tips that, just new type of tips that we have discovered in the last decade. And I'm just going to go over some of those. So the first one is the design time is really crucial. At the design time, you need to start designing what availability means for a system. You need to set availability indicators and your objectives, and this is where you actually also start thinking about how you're going to collect. If you care about latency for availability, you start planning how to collect the latency data, what instrumentation library you're going to use, what is sort of the performance impact. You start doing that at the planning period, at the design time. So you can say that availability is a part of the design, is the initial design. It's not something that you think about at a later time. And you need to make sure that like multiple people are involved in. You need to, for example, make sure that operators are involved in the discussion phase, so they can give you feedback. We have this like quiet collaborative review at Google that SRE is actually going through some of the the aspects of production experience before we put things in production, so they can point out easily like, hey, this seems like like either it's a bad design, or you can just improve it, or like they can give you really good tips because they know how to operate systems more than software engineers. And if your systems are large, there's a really large number of like service dependencies, and your stack is really complicated. And you want to have better strategies to understanding who is contributing to what. For example, at my company, again, there's lots of like services depending on each other, and the storage service is like at the bottom of everything. And storage services usually having lots of outages. It's so hard to figure out who's contributing to those outages. What type of like high-level services are actually like misusing or overusing, or like there's some capacity problem related to that usage. In order to be able to understand that, we actually like collect really high cardinality data, and we can figure out what is the origin of this request, and like why there is latency in this particular cases. I'm not going to like talk a lot about this topic because it's a huge topic, but I gave another talk on this subject before, so you can take a look at the link on the slide. But the core idea here is really figuring out who is contributing to what. Especially it's really important for infrastructure stuff because they're always at the bottom and everybody's relying on them. I want to be able to tell easily, or it could be like even like really simple business type of analysis. You can easily say that like who has more impact on my storage or my DB? Is it the mobile client or is it the web client? So you can like predict maybe like capacity, and like you can troubleshoot issues, and you can understand who is being impacted when there's an outage. Another complicated, I think, outage response problem is jumping between different datas. In this case, it could be you have some monitoring data, you're looking at some dashboards, but they don't tell you much, right? Like you also have been collecting all these like logs and traces and some other stuff, and you want to be able to like quickly jump between back and forth. Even between like traces and logs, you want to be able to see what is going on. And at an outage time, just believe me, even though how simple it looks, it's just really complicated. You make a mistake in the query, you just like end up like putting like, you don't escape one little thing or whatever, and being able to access the data can be really complicated. So we want to make this type of correlations really easy. If there's an incident, so recently we've been working on this exemplar project. We collect our monitoring data and put them on dashboards, and then we just actually put these stars, and you can just click on them, and like it takes you to the logs, it takes you to the traces. If there's this like unlikely, for example, latency event, give me the trace so I can take a look, or give me the log so I can take a look what actually happened there. It is really has been a good strategy for us because it really removes the friction. You can easily jump back and forth, and the operators just don't feel like there's like some additional work in order to take a look at some other debuggability signal. And we want to make like on-call debugging so much easier. This is a huge issue because you rely on multiple things, and we usually use distributed tracing. So this is a distributed tracing UI. What it does is like all these bars are representing some amount of work. They can be coming from like different processes. So it could be a multi-service environment, and it allows you to kind of like figure out like, hey, there's like this latency for this type of thing, and like there's like some errors coming from this service, and you can just see the lifetime of a request, a user request, even if it touches multiple things. So you can see everything end to end, and you can see what fails, what just kind of looks like there's more latency. And from this data, we actually want to be able to say, it's really possible to say that like, hey, if there's a problem with this particular API server, thing, who am I going to call? I'm an SRE. I don't understand much. I can maybe take a look at the code. I can try to understand what was going on. I can look at like the networking and other stuff and rule out a lot of like common stuff. And then at some point, I may need to actually call the people who are working on this project. So if you can make distributed tracing or like logs collaborative in a way that like you can actually pinpoint to the right person, that is kind of making all this escalation really easily. And it's a lot of like stress for a lot of people to figure out like who to call when there's an issue, or they're sometimes like not willing to call because they're not even sure. But this kind of like this type of tools and being able to map this type of data to like actual people makes us more confident. And we've been really strong on this idea that the data you collect should be more dynamic. Like it shouldn't be baked in the. For example, imagine that enabling more data collection in production was possible just with configuration. Just by like there's like a, the panel or something, you can just change the configuration, push it, and dynamically it enables more collection. Then operators can actually enable more data collection and to dig further without like actually calling the engineering team to figure out what. So we have this culture of like living as much as instrumentation possible, but making it as cheap as possible if the collection is not enabled. If the collection is enabled, at some point we start collecting and it's becoming expensive, but we only enable it if there's a real issue. And then once the data is collected, once we actually figure out what is going on, whatever, we turn it down to reduce the cost. Such capabilities really help the SRE, the operations team to move faster without relying a lot on engineering. One of the other aspects is this like fleet-wide collection. One typical example of this is our continuous profiling. Our continuous profiling is just imagine a CPU memory profiler continuously collect and profile samples once a while from all production services. So you can actually see all these like company-wide hotspots. So this is really nice because you can generate reports. Like you can say that like, hey, these are the most latency-sensitive components, or these are the most expensive calls. If you have engineers who wants to like optimize some stuff, like they can actually only focus on those like high impact type of work. Fleet-wide reports also helps teams to understand if they are impacting other teams' work, and it's really quite they're really useful to analyze. Before landing, for example, performance impacting changes. I have a library, I'm just completely re-implementing the behavior, and I want to see who is actually using it. So I will be able to estimate what is going to be the overall performance cost. And there's one more thing that we really like, and I haven't seen it elsewhere. These are these introspection pages. At Google, there is this culture called Z pages, and every server just exposes some Z pages. Z pages are debugging. Like they look terrible because CSS, we don't know CSS much as distributed, I think systems monitoring people, but these are like little dashboards, and it kind of like explains what is going on in the process. It collects, it displays the data it's collected in the same process. This is an example for the traces collected inside one process. So you can actually, like anybody without knowing anything about monitoring stack of that particular team can go to these pages and see what is going on. This is nice because you don't really have to there's one at least last resort to look at if you don't know anything about the monitoring practices of that particular team. Also, it's kind of nice because if you kind of fail to export data from a particular service to the actual monitoring backend, you can still see what is going on. You can see that you fail to export that type of data. So this is kind of our last resort, and we like it, and they're really useful both in production and during development. And they're just allowing you to initially inspect what is going on. So to conclude, I want to say that, like, failure is going to happen. You shouldn't make failure an exceptional case. And there are, 3 main aspects that help you to be prepared for failure. And by enabling some of the more collaborative processes or tools, it actually helps you a lot. And I think the fundamental problem that we don't really see failure as something expected, and we don't see the incident response as a collaborative thing. So I just want to, I hope that I change your mind about these two. I just want to thank you for your time, and I can answer your questions right now. Also, feel free to reach out to me. I'm responsive to emails, and I'm also available usually on Twitter.
Thank you so much for the talk. It was really great. So far, we don't have any questions from the audience. Anyway, if you want to make a question, I can go and give you the microphone. Just raise your hand. I have one small question. My question is, if a server designed failure-proof needs an update, which are the possible issues to consider and solutions regarding...
What is failure-proof?
I mean, if it is designed to prevent failures...
Oh, so it's like a super resilient type of system.
Yeah, let's say that. So what could be main issues to consider and solutions if it needs an update?
When you're upgrading to a new version.
Yeah, for example, with extra functionality.
So it's you shouldn't really think about a particular server as a self-contained problem, because it relies on all the hardware. It relies on all the underlying layers. It relies on, for example, the kernel, the networking stack, and everything. So we tend to actually not think about trying to super optimize and make things resilient in the self-contained way. We try to actually build more self-recovering systems. Like if there's one process failing, we can just schedule another one here, and this layer is mostly stateless, so it's just so much cheaper to just kill it and start something new. Because once you start to think about hey, I really need to keep this up and running, you need to touch all these other layers that you have no control of, right? The hardware failures happen all the time. Network specifically fails a lot. And you basically have no control over the underlying stack. So I think the right approach is not to overthink about, this is not something you're going to Mars. And even if you're going to Mars, you're actually it's funny because lots of these probes have multiple implementations of the same thing running at the same time, and there's a voting system. They're all trying to calculate the same function, and the voting system decides I got this result, but one the other result. So the same result wins. So I think my approach would be more of understand the failure is not that. In this case, I would approach the problem differently.
Okay. And what do you think that will be the next generation of monitoring issues and failures for servers?
I think there's a lot of work going on in terms of collecting, event data and tracing data in a more high volume and verbose way. If you've been watching the observability space, there's more of I think work being done in order to let's collect this type of data consistently, and let's try to have end-to-end data collection. I've been involved in 2 standard-ish type of projects. The first one is having end-to-end distributed traces, so we will have a W3C header standard soon. So you will be able to have end-to-end traces, and we will be able to go to, hey, MySQL, can you just implement this header format so people can actually follow the traces and export some data. And the other thing is I think the instrumentation libraries should, there used to be multiple instrumentation libraries, and we're trying to converge everything into one thing so we can have consistent collection all across, and consistent practices maybe when it comes to collection. So there's some, I think, work in order to gather better signals, because that's kind of like what is missing right now. Like, yes, there are a lot of vendors, there are a lot of like good tools in terms of visualization and analysis, but the data is not there, and like that's the initial thing that we need to fix.
Thank you so much. Do we
Any
have any
other questions? I will be also around here, so feel free to come and ask.
Okay.
All right, thank you.
So, thank you so much.